We now begin the best paper session. This best paper session was a selection from the 2020 papers submitted last year, and with Carlos and with the help of topic chairs, we selected among the best papers. Today we will begin by the second prize, so a talk coming from Melbourne. So the best paper that we will first hear is called a data-driven frequency scaling approach for deadline-aware energy-efficient scheduling on GPUs. This best paper will be presented by Shashikant Ilager. It's with his co-authors Rajiv, Kotajiri, and Rajkumar. So Shashikant, I see you are here. Good morning, or I don't know, good night for you. I don't know. Yeah, good afternoon. Thank you for presenting. So we let you begin your presentation. So Shashikant, you were a PhD student in Melbourne, I suspect, when you submitted last year. And now you are a postdoc. You are in a postdoc position in University of Melbourne, and you're working on distributed systems and machine learning. So the floor is yours. You can share your slides. Please remain in between 15 to 20 minutes of presentation. I ask everybody to put questions in the Zoom chat so we can ask the question lively, and we will have a short live question and answer session after that, and you receive the prize. Shashikant, the floor is yours.
Thank you very much. Thank you, Laura, for introduction. Good afternoon all, and good day for others who are based on your time zone. I'm Shashikant Ilager. Today I will be presenting my paper, a data-driven frequency scaling approach for deadline-aware energy-efficient scheduling on GPUs. This work was accepted as part of CC Grade 2020. In this talk, I will briefly introduce about my problem, then go over the motivation of this study, and I will talk about our system model as well as our solution approach. Then I will introduce few of the results from the paper. Then I'll conclude my paper with my talk with the observations we found in this work. GPUs, or predominantly we call it as a graphic processing units, has been used in many decades, mainly for accelerating the graphics rendering. It has been used for in tandem with the CPU, where a CPU can offload any graphic acceleration and it can perform the parallel graphics rendering and get back the result to the CPU. But thanks to its parallel architecture, which follows a single instruction and multiple data stream, lots of application, not only a graphics rendering, different general purpose application have been finding their way to execute on GPUs, which we generally call as general purpose graphic processing units. Workloads like AI or ML or HPC workload, where we need to run a large number of computation in parallel, and GPUs make more sense to run there since they can give a higher throughput. Not only the scientific application in HPC or training mechanisms in AI ML, we have been seeing the adoption of GPUs even in domains like crypto mining and other aspects. As the applications domains for GPUs are increasing from graphics rendering to general purpose application, they are becoming more ubiquitous, and they have been adopted in cloud data centers as well as the HPC data centers. For instance, almost all the top 500 supercomputers have been boosting their teraflops of performance by introducing more GPUs in the system compared to the CPUs. However, despite of this increased usage, the bottleneck to build hyperscale GPU system, just like any computing element, has been the power consumption. Each GPU consumes around 200 to 300 watts of order of power, and each node in a data center may have 8 or even tens of GPUs equipped within a server. So this creates a massive bottleneck to build hyperscale GPU systems. On the other hand, workloads we often run on GPUs are becoming more sensitive to the SLAs or quality of service parameters such as a deadline or their execution time, which often require to run faster and spend more energy. So what has been the motivation for this particular study? When we say the energy efficiency for GPUs, one can address this with a different abstraction layer in resource management, either at the middleware layer where we can come up with a better resource management solution across the data center, or at the lowest abstraction layer in the device itself, how can we manage the power in a better manner? In this paper, we address this energy consumption issue at the lowest abstraction layer that is at device level. So any power consumption, just as a CPU, we have two components that affects the power consumption of a device. One is a static power consumption, another one is a dynamic power consumption. While static power consumption mostly deal with the leakage of current in the circuitry, which has been addressed with the proper proper device architecture, as well as the low power management or sleep state management that tries to avoid this leakage of current in the circuit. But nevertheless, large amount of power still has been spent in dynamic power that is based on the usage level of that particular device. And the dynamic power, the most prominent method to manage has been dynamic voltage frequency scaling. Based on the usage level, we do vary the frequency, so does the voltage varies, and which affects the overall power consumption. In particular, GPUs have two frequencies. One is a core that mainly regulates the streaming multiprocessor, which each GPU may have thousands of such streaming multiprocessors, and that mainly controls the registers or the components like texture cache, shared memory, L2 cache, all of these processor elements. And we have one more frequency, which is a memory frequency, which mostly governs the bandwidth of DRAM, which is a critical component in any GPU where we get the data from CPU to GPU and vice versa. And particular to GPU, there can be a multiple memory frequencies as well as multiple core frequencies. Let's take an example, popular GPU that is NVIDIA GTX 980 that has total 87 core frequencies in the range of 324 to 3500 megahertz, and we have around 4 memory frequencies with the stated range. And it's important to note that not all memory frequency supports all the core frequencies due to the limitations into the voltage operating difference between memory and core. But nevertheless, we still have around 266 possible frequency combinations in where one can set these frequency for application execution. And all the vendors do provide libraries where we can control and configure this frequency configuration of each of these machines. So the common notion of any DVFS is I increase the frequency so that I decrease the execution time, and that will eventually increase the power consumption, which we can see this in this particular application when we executed on one of the GPUs. So where this application, when I range core frequency from 600 to 1300, then obviously the power is increasing mostly linearly and the execution time is decreasing, which is perfect for few of the application, but it is not true for all the application. Consider application case A. While I increase the frequency, the execution time is decreasing as we expect, but the linear expectation that power consumption will increase is not true. It is kind of a random at some point. The similar is the case for application C, where the power consumption is linearly increasing as we increase the frequency, but there is no correlation at all with the execution time. In worst case, even it has a negative effect on execution time of this application when we increase the frequency. And some application will completely have a random behavior with respect to frequency as well when we increase the frequency or decrease it when compared to power and execution time. So this is mostly to do these non-linear relationship mostly is to deal with the resource usage characteristic and the stalls they induce individually in these application kernels. So the existing approach mostly go with the linear scaling, where if we want to speed up the application execution, we increase directly to the maximum possible frequency, assuming that it will execute faster and give us a energy efficiency also. But we observe based on our initial study that it is not true for all the application, while it is true for some of the application. So our objective is we want to reduce the GPU energy consumption by efficiently scaling the frequencies in application execution. So how do we approach it? We have two main contributions. One is prediction models that are built to predict for given frequency what would be execution time, as well as its estimated energy consumption. And we use these prediction models for scheduling algorithms that finds schedule sequence and scales the GPU frequency for energy efficiency. So how exactly we build this particular framework. This framework consists of two parts. First one is a predictive modeling, and the second one is we use these models for resource management aspect, and particularly we target scheduling. So our prediction modeling consists of two phases. One is we build the training data, then we use that training data to build the prediction models. The training data mainly consists of three parts. Suppose we have a number of frequency combinations supported by GPU. We run a profiler. That profiler will run applications on all possible frequency configuration, and we get all the profile data, including whatever parameter that particular GPU provides us. And along with this profile data, we read what is the corresponding energy and execution time data and the frequency configuration we have used that particular set of profiling. All these three components builds a training data, then we use it to build energy and execution time models. So to build this training data, we did work with the two benchmarks which are popular in GPU domain. That is a Polybench and Rodinia, which consists of 12 applications of different domains, including biological simulation or medical imaging. And we also have some basic mathematical computation applications like covariance computation, correlation computation. And it's important to remember that all of these basic computations are part of almost all AI or ML workloads, where at the end of the day, irrespective of algorithm, at the machine level, they will do all these matrix operation, including transpose or the matrix multiplication or vector operations. So it is important to find a better frequency scaling for this lowest level application abstraction in order to find energy efficiency even at a higher abstraction layer of different application. So we did use a Grid 5000 testbed, which is an experimental testbed for mainly designed to evaluate the energy efficiency of different scientific applications. And in particular, we used Tesla P100 GPUs. And for each configuration run, we did get 120 features. And for all the applications, we built this test data, and we tried different ML models. It is no brainer that as we target to predict execution time and power consumption, they do require a regression model. So we did try different regression models, including linear regression, lasso, and different gradient boosting algorithms, including XGBoost and CatBoost. So based on our experiment, based on our training data and the models we have used, we did found that CatBoost performed well for particular training this data set, with the root mean square error of 0.38 for energy and for time 0.05, showing also the fact that it is more difficult to estimate the energy consumption, and it has more nonlinearity compared to the time prediction looking at the RMSE values. The part of reason CatBoost has performed well also due to the fact our training data set out of 120 features, around 5 to 10 features had a categorical data, and CatBoost has specially designed to transfer in an efficient way the categorical features into a numerical data without losing their importance. That's the main reason CatBoost has worked better in particular to our training data set. So, and we did study what are those actual features that actually matter to this particular outcome in energy and time prediction. Out of 120 features, our study has shown that 20 features are dominating, and they are more than enough to estimate a reasonable accuracy of outcome. For example, to find the x-axis shows all the 20 dominant features, including what's the clock and what's the L2 read hit rate, what is the IPC, or that's inter-process communication mechanism, all that metrics. And the y-axis shows what would be the loss, or that is RMSE values with or without this particular feature. So based on that, we could also see that for time model, the features that are morely related to IO, that is DRAM write transactions, plays a significant role, which is not present in the energy model. So indicating IO features have a bit more higher coefficient in time prediction models. So once we have these prediction models, we would like to use it for, these prediction models could be used for different resource management aspect, but we use it for scheduling purpose, where this particular model considers what would be the KOS parameter that we consider as a deadline here. Then a scheduler would look for what should be the better possible frequency combination out of these hundreds of combination. And we configure that particular combination before the execution, then we execute that application. We also use clustering in order to, if the new application arrives out of the knowledge database which we have used to train the data, then we use it in that case to correlate to existing application and use the prediction models of that particular applications to directly use it for scheduling without using them in the training. So the problem is modeled in this particular way, where we have n number of applications. Each application has different arrival time as well as deadline. And all of those applications follows their own power and execution curve. For example, some may have a linear where increasing the power decreases the execution time, but this may not be true based on our motivational study I have shown earlier. So our intention is to find that point where we will have the lowest power as well as the fastest execution, which we could find based on the frequency configuration. So the overall idea is once we execute this n number of application, I would like to decrease the total power consumption of the GPU. So we did propose a simple algorithm in a simplest form. It initially sorts all the jobs based on their deadline. Then for all the possible clock frequencies, we do predict what would be the estimated power as well as the execution time. And if the execution time meets its deadline as well as it has a lowest power consumption, then we set it in the runtime, that particular frequency, then we execute this application. So going over a few of the results in this study, in this particular graph, we have different applications on x-axis and the power consumption on the y-axis. Our proposed method DDVFS, as you can see, has the lowest power consumption compared to the baselines, that is a default clock and max clock that NVIDIA driver usually uses to speed up the computation, as well as if there's in a normal environment, it does use a default clock in our configuration. So in total, when we take an average of all this total schedule of our system, we did have 15% less energy consumption compared to the best performing model, that is default clock, that is around 330 watts of total power for this only small set of applications. So to analyze how the frequency scaling has been worked in the scheduling process, as we can see, our application, our system scales the application frequencies based on its requirement. If the application has a stringent deadline, it can scale well above the lowest possible frequencies. It is important to know that these, even though our max clock is still the lesser than default clock in our particular setting. And to analyze how the deadline has been achieved, this is a normalized time graph where the red dots are all the deadlines of each application. And these green dots are the completion time of our method, that is DDVFS, and blue and red are for default and max clock configuration. So as we could see, all the applications have executed well before the deadline. And in some cases, some applications have even executed before the max clock configuration, indicating the fact that having the maximum clock all the time may not be benefit for all the applications. In worst case, it may only increase the power as well as the execution speed, execution time of that application. So it is important to find or scale the frequency based on what suits for that particular application. To analyze how the prediction models have fared in runtime, we did find what is the predicted value before the scheduling and what is the actual value we got after the scheduling of that application. For instance, in this particular power graph, where we have this blue line, which is the actual power consumption, and this is the red line, which is the predicted power, which we used as a reference for scheduling. As you can see, the predicted power has closely followed the graph of actual power that has been consumed by each of these applications in the execution. Similarly, for the time, the predicted time closely follows the actual execution time in the scheduling when we use it for schedule all these 12 applications. To conclude the observation we found in this study, application kernels, especially the GPU kernels, behave differently for different applications. More so, even if the similar clock setting, they will have a different power curve as well as the execution curve. This is mostly to deal with their resource usage characteristics, how they interacting with the IO module as well as the compute module, all that aspect. So the simple heuristics where if I simply increase the scale frequency would increase my speed up or give a higher throughput will not be true for all the cases. Whereas data-driven models can accurately help us to build a frequency scaling mechanism and achieve the energy efficiency. Moreover, the one use case which we have shown is a frequency scaling, but such data-driven analysis not only helps for resource management, it can also help for system architecture to find what type of applications are using what type of system module at the device level, and they could use it to design the system in the future for better management. For example, all the modern compute element like tensor processing units, they do implement optimized matrix multiplication circuits inside the hardware that would speed up their execution in runtime when you use a tensor library. Such things can be done with this general purpose libraries as well. If we know that for this particular computation, if I have a matrix transpose with this input size, this would be a better frequency. If such an feedback has been given at the device level, so any application that runs on such an optimized device would yield better energy efficiency as well as the speed up. So if you are interested in software repository, including all the profiling scheduling that is built on top of this particular infrastructure, you could check out here. Thank you.
Thank you, Shashikant, for this very nice presentation. Dealing with energy efficiency and GPU is not an easy task, and it was very, very clear. I received several questions, so if you can reply quickly to some of them. So the first question is how to optimize SLA violation cost?
How to optimize?
Yes, SLA violation cost.
SLA violation or duration?
Violation.
SLA, okay, so the SLA is first what SLA we have been considering, it completely depends on that. So in this case, if we are considering the execution time, so obviously we try to meet those execution time, but the SLA completely differs for different applications. Most of time in the GPUs, it is mostly execution time, and always if it comes with the cost, then cost in the managed services like in a cloud, we always give the cost as an input. I want to run this application within 2 hours. But if you talk about general applications like web service and some other class of application, their SLA is mostly about response time. So we have to come up with the metrics that optimize for that particular SLA, which we are targeting that application. So if I'm not wrong, in this particular application, I did use execution time as a QoS or SLA constraint. So we have to make sure we execute within that particular metric which we choose.
Okay, thank you. One question from Kunal. Why the execution time does not reduce when you increase clock frequency for all applications? What is the intuition between that?
Yeah, good question. So that's what most of us expect, that if I increase the clock, it will decrease the execution speed, which will be true for most of general application. But there are some special class of application, or I can say kernels in terms of GPUs. Those kernels may be having more IO dominated. So it doesn't make sense I keep running for that application with the highest frequency while it may waiting for particular IO part to be return some data. So these things cannot be generally classified. So we have to understand, okay, this application spends more time maybe on IO or waiting for some other subroutine to give the data. So it makes sense to run at a lower clock frequency rather than keeping the clock high and that application is doing nothing useful computation. This is one intuition. So there might be a different application level complexities as well. Sometimes we cannot describe it for each and everything. That's why these data-driven models can capture such behavior.
Thank you. A question from Mael. In the graphs we were seeing, was it the power consumption of only GPU? Have you also studied the power consumption of the full system as well?
Yeah, this is not the power consumption of full system. So this is the only power consumption of GPU device, which NVPro provides us that profiler tool. In order to consider the full system, we would also need to consider that problem where we partition the data and what amount of computation is used in CPU as well as the GPU. But this particular work, we only consider power consumption of GPU, not the whole system.
Okay, thanks. And one last question from Muhammad. Frequency scaling will definitely affect the application performance.
Yeah.
How about its energy overhead, in particular when frequency switching occurs very frequently?
Yes, so frequency, we can target at a multiple level this particular aspect, that inertia that may come up with the frequency scaling, but doesn't matter whether we do it or not. Most of the time when we submit our application, our device will always be at the lower frequency. At least if they go with the max clock, it will switch one time. And we are also saying the same thing. We are not switching every time. We are switching one time for that particular application, because we are not dealing with the higher level libraries. We are dealing with the basic computation of that particular application. So if our framework includes multiple frequency switching, then we have to do the study. Does it make any sense to switch how many times and all that? But in this particular framework, we are switching only once, which is also the case for max clock or default clock.
Okay, thank you. And one last question from myself. Did you continue to work on this subject after your submission in 2020 at CC Grid? Did you advance on some aspects?
I am still working on energy efficiency, but not directly working on only GPUs. Now I am more concerned about a middleware level at higher abstraction, like if you have multiple nodes, how can we do the scheduling or the provisioning, those aspects of part, but not at an individual GPU level, and the current work is not concerned with that.
Thank you, Shashikant. Okay, so I would like to share my screen for this official moment. So I hope you can see my slide, Shashikant. So this is the official moment where you receive officially the second prize for the Best Paper Award of the CC Grid 2020 conference. Congratulations to you and all your co-authors. So everything is virtual, so you will receive the PDF. It's just a PDF plaque, but congratulations. I see a lot of people applauding through emoticons and things like that.
Thank you.
Emoji. And yes, thanks, Carlos. Yeah. And more concretely, you will also receive a real prize, some money. So Raj, you confirm the Best Paper Award will consist of $500 of money prize for Shashikant and his co-authors. You confirm that, Raj? Yes. So Raj, is $500 US dollars or Australian one? We don't hear you, Raj. We don't hear you. You are mute. I hope for you
virtual dollar.
Virtual dollars. Okay. No, we need real money for students. Okay. So
Bitcoins, we'll give Bitcoins.
Congratulations, Shashikant. Congratulations for you. And thank you for this very nice presentation.
Thank you very much. Thank you.
We are now going, thank you, and good continuation.